In the last lecture, we have gone through the introduction of digital filters, and we have classified filters into two parts: IIR filters and FIR filters. IIR filters are infinite impulse response filters, whereas FIR filters are finite impulse response filters. Today we will go through one filter, and the type of that particular filter is FIR filter. As we already know, digital filters are characterized into two parts, FIR and IIR. First we will discuss FIR filters, then we will go towards the IIR filters, right? So these filters will have finite impulse response, as we have already discussed multiple times. So we can write it like this. So if there is an input, xn goes through a system with hn, output will be yn, then yn will be equal to xn convolution hn, that is equal to summation n equals to 0, that is k equals to 0 to m minus 1 hk x of n minus k. In this case, this hk is defined for m unit samples. Okay. Now if we take Z transform of this difference equation or this convolution, we will get yz will be equal to summation k equals to 0 to m minus 1, hk z minus k into xz, and that will be equal to yz equal to xz summation k equals to 0 to m minus 1 hk z minus k. That is hz is equal to k equals to 0 to m minus 1 hk z minus k. Now an FIR filter will have a linear phase response, and a FIR filter will have linear phase response. The importance of this linear phase response we have discussed multiple times in last few lectures, and that will be defined by the group delay tau g is equal to minus del of theta omega by del omega should be equal to constant. That is the required condition for having linear phase response. That means this theta omega should be linear function of omega, then only this tau g will be equal to constant. So this particular condition we have to make true, and this is the property of an FIR filter. So the necessary condition for an FIR filter to be linear phase if the unit sample response satisfies the condition that is Hn is equal to plus minus h m minus 1 minus n, where n is equal to 0, 1, 2 up to m minus 1. Now this plus minus sign is the case for symmetric sequence and anti-symmetric sequence. For symmetric sequence, Hn will be equal to h m minus 1 minus n, whereas for anti-symmetric sequence, Hn will be equal to minus of h m minus n minus n. So these two sequences are also called even sequence and odd sequence. Okay, so one can clearly see this m, number of samples, m can either be odd or even, and we have two kinds of sequences. One is symmetric sequence, another is anti-symmetric sequence. That means we have total 4 possibilities. Then we have total of 4 possibilities. So we will go with this. So first is called type 1 filter. In this case, m is odd and Hn is symmetric sequence or even sequence. Next is type 2 filter. In this case, m is even and Hn is anti-symmetric sequence. Third is type 3rd filter. In this case, m is odd and Hn is in this case m is even and Hn is symmetric sequence, and in this case m is odd and Hn is anti-symmetric sequence. Type 4 filter is M is even and Hn is anti-symmetric sequence. Now we'll see how the sequence will look in this case. Okay, so first case, let M is equal to 3. We are going for a very small sequence. Then this is N, this is Hn. Okay, so for any values, so our sequence will be like 0, 1, 2. So then it is like this, and so it is having a symmetric sequence across this central point, that is 1. Okay, next we'll see for type 2 filter. In type 2 filter, let M is equal to 4. In that particular case, Hn and this N, so we'll have 0, 1, 2 and 3 points, 1, 2 and 3 points. Then we'll have a sequence at this point, then at this and this. Okay, so this is also a symmetric sequence with M even. Next is for type 3 filter. We want to see the sequences, right? In this case, same, let M is equal to 3. So we'll have N, Hn, 0, 1 and 2. So at 1 it should be a 0, and but at 2 it should be equal to this particular point. So this is type 3 filter with anti-symmetric sequence for M equals to 3. And please note that this particular center point has to be 0 to make this sequence anti-symmetric. Okay. Next is type 4 filter, and in this case M is even. So let M is equal to 4. So we'll draw it again, and we'll have a sequence for Hn, N, and this sequence has to be antisymmetric with M equals to 4 at this point. Then it is this point at 0, 1, 2 and then 3. So it will be like this and this. So now this is also a M with even and antisymmetric sequence. So this is for a type 4 filter with Hn. Now we want to see the frequency responses of all the filters. Right? This we want. So first one is, we'll go for type 1 filter. Case is M is odd and sequence is symmetric. That is, Hn will be equal to H of M minus 1 minus N. Okay. Now we want to realize this particular system, type 1 filter, and we know Hz is equal to summation k equals to 0 to m minus 1 hk z minus k. Right? We know this from the previous equations which we have seen. Now we can break this sequence because m is odd, so we can break this sequence into two parts, that is k equals to 0 to m minus 1 by 2 hk z minus k plus k equals to m plus 1 by 2 to m minus 1, then hk z minus k. Okay. Now this sequence goes from k equals to 0 to m minus 1 by 2, but this sequence goes from m plus 1 by 2 to m minus 1. Right? So what we can do is we can start this sequence from k equals to 0, and it can reach also to the same point because it contains the same number of samples as this sequence. So we can also write this particular sequence in terms of k equals to 0 to m minus 1 by 2. For that particular case, we have to find out the difference between these two. So that is m minus 1 minus m plus 1 by 2 will be equal to 2m minus 2 minus m minus 1 by 2, which is equal to m minus 3 by 2. So that's mean if we rewrite this equation in the form summation k equals to 0 to m minus 1 by 2 hk z minus k plus summation k equals to 0 m minus 3 by 2, but then this hk will be changed from m minus 1 minus k to z minus m minus 1 m minus 1 minus k. I'll just rewrite this again so it could be much clearer. So minus m minus 1 minus k. Okay. So we have rewritten this equation in this form. By using the symmetry property of linear phase FIR filter, this h m minus 1 minus k will be equal to h of k, because this is a symmetric sequence, right? So then this equation can be written as summation k equals to 0 to m minus 1 by 2 hk z minus k plus summation k equals to 0 to m minus 3 by 2 hk z minus m minus 1 minus k. Now these two parts of this equation can be easily matched if we can put it like this: k equals to 0 to m minus 3 by 2 hk z minus k plus z minus m minus 1 minus k plus h of m minus 1 by 2 z of minus m minus 1 by 2. Okay. So now this comes out to be a very important equation of Hz. And if we can take this z to the power minus m minus 1 by 2 common, hz will be equal to z to the power minus of m minus 1 by 2 h m minus 1 by 2 plus summation k equals to 0 m minus 3 by 2 hk. Now this z minus k, is actually z minus k into z m minus 1 by 2, because we have taken z to the power minus m minus 1 by 2 common. So then it will be z k minus k plus m minus 1 2k by 2. So we can write it this equation like z m minus 1 minus 2k by 2. Similarly, for z to the power minus m minus 1 minus k z to the power m minus 1 by 2 will be equal to z minus 2m plus 2 plus 2k plus m minus 1 by 2, which is equal to z minus common m minus 1 minus 2k by 2. So that's mean we can substitute this particular part here. So it will be plus z minus sign m minus 1 minus 2k by 2. Okay. Now this is the transfer function in terms of hz we have obtained. We have obtained this transfer function in terms of hz, right? Next we want to we'll remember this particular transfer function and use it in further cases. After we will discuss type 2, type 3 and type 4 filters. Another case is type 2 filter. For the case of type 2 filter, m is even and hn is symmetric sequence. That is hz is equal to summation k equals to 0 m minus 1 hk, and then it is z to the power minus k. Now again, as we know, we have to divide this sequence into two parts. So as m is even, so m minus 1 is odd, so it will be k equals to 0 to m by 2 minus 1 hk z to the power minus k plus summation k equals to m by 2, because m is even sequence, to m minus 1 hk z minus k. Now applying the same part as it is going from k equals to 0 to m by 2 minus 1. We also want to find out this equation, this particular series goes from k is equal to 0 to some value, and we have to find out that particular value. We want to represent the same in the sequence from k equals to 0. So then m minus 1 minus m by 2 is equal to 2m minus 2 minus m by 2, that is equal to m minus 2 by 2, and that is equal to m by 2 minus 1. As it is a even sequence, that's why these both terms come out to be same. So then we can represent this equation as k equals to 0, m by 2 minus 1 hk z minus k plus summation k equals to 0 to m by 2 minus 1 h m minus 1 minus k into z to the power minus m minus 1 minus k. Okay? Now this particular sequence we already knew this h m minus 1 minus k due to the symmetric property of linear phase FIR filters, it will be hk. Then this is equal to k equals to 0 to m by 2 minus 1 hk z minus k plus z to the power minus m minus 1 minus k. Now doing the same thing and taking z to the power minus m minus 1 by 2 common, it will give k equals to 0 to m by 2 minus 1 hk z minus k z m minus 1 by 2 plus z minus m minus 1 minus k into z to the power m minus 1 by 2. Minus 1 by 2. Okay. So writing this equation, z minus m minus 1 by 2, that is equal to k equals to 0 to m by 2 minus 1 hk, and we already have solved this particular terms, so it is z to the power m minus 1 minus 2k by 2 plus z minus m minus 1 minus 2k by 2, as we have seen with the previous case. Now this is hz for the type 2 filter. Next we will discuss for type 3 filter. Type 3 filter. In this case, m is odd and hn is anti-symmetric sequence. That means hn is equal to minus of hm minus 1 minus n. And if we see, this type of filter has only a difference with type 1 filter with a minus sign, because this sequence is anti-symmetric sequence. So we can write directly the hz we have obtained for type 1 filter, that is hz is equal to z to the power minus m minus 1 by 2 summation h of m minus 1 by 2 plus summation n equals to 0 m minus 3 by 2 hn z m minus 1 minus 2k by 2 and z m minus 1 minus 2k by 2 with a negative sign. Now there is what could be the sign in between these two sequences is? That is the only difference, and that comes out to be negative due to this part with a negative sign. So this is the only difference between type 3 and type 1 filter. For m is odd, where in type 1 hn is symmetry sequence, this particular term is positive, and in this sequence it is negative. So I will just mark it in red so you can see this particular point. This is the only difference between type 1 and type 3 sequence. Sorry. Next is type 4. In this particular case, m is even and hn is antisymmetric in nature. Then one can see it is relevant to match type 4 with type 2 filter, where for type 2 filter we have hz is equal to z to the power minus m minus 1 by 2 summation n equals to 0 to m by 2 minus 1 hn. This is actually summation z to the power m minus 1 minus 2k and then z to the power m minus 1, it is by 2 minus 2k by 2 with a negative sign. And for this to be an antisymmetric sequence, there will be a negative sign here. So these are the 4 transfer functions of type 1, type 2, type 3 and type 4 filter. Now most of the cases in further analysis will take the sequence. In most cases, if there is their characteristics is quite common with a negative sign or positive sign, then we will discuss only one sequence. And if there is a relevant part we have to discuss one by one, then we will discuss all the filters all together. Next part is, if we want to multiply this particular sequence, which we obtained for type 4, and we call this particular sequence is equation number 1, and we are interested in this particular equation, and we can see this particular property which we are telling right now is valid for all 4 filters. Either they are symmetric or antisymmetric with even sequences or odd sequences. So this is important. So we are just going for this particular equation which we obtained for type 4, and we are telling it to be equation 1. So if we multiply this particular sequence with, if we substitute, first step is, if substitute Z inverse instead of Z, then Hz will be H of Z inverse. It will be equal to Z m minus 1 by 2 summation n equals to 0 to m by 2 minus 1 Hn and Z minus m minus 1 minus 2k by 2, and then there is a negative sign, and then there is a Z m minus 1 minus 2k by 2. Okay, so we have substituted Z inverse instead of Z. Then Z inverse will be equal to Z m minus 1 by 2 n equals to 0 to m by 2 minus 1 Hn and this particular value. Now if we multiply this particular sequence, multiply the equation, sorry, not sequence, so actually the sequence, but we are writing multiply the equation by Z to the power minus m minus 1, then it will be equal to Z to the power minus m minus 1 h of Z inverse equals to Z to the power minus m minus 1 by 2. Okay, and that again summation n equals to 0 to m by 2 minus 1, and if we take negative sign common, it will be Hn Z m minus 1 minus 2k by 2, then negative Z m minus 1 minus 2k by 2. And if we see from equation 1, if we compare with equation 1, that is this equation, we can see this Z to the power minus of m minus 1 h Z inverse is equal to minus of h. Now this particular part is true for anti-symmetric sequences. That is type 3rd and 4th filter. And one can easily see for the symmetric sequences it will be Z minus m minus 1 at Z inverse will be equal to h, and is true for symmetric sequences. Symmetric sequences are also called type 1 and 2 filter. Now what does it signifies? What this particular property signifies? This property tells that the roots of Hz inverse and Hz are identical, and that's mean the roots of Hz must exist in reciprocal pairs. That's mean, for example, if Z1 is a root, or we can say 0 of Hz, then 1 by Z1 is also a root. then 1 by Z1 is also a root. Further, if the unit sample response Hn of the filter is real or complex value roots, they must occur in complex conjugate pairs. That means if Z1 is complex, then Z1 conjugate is also a root. This is the complex conjugate of Z1. As a consequence, 1 by Z1 conjugate is also a root. And 1 by Z1 complex root also a root. Okay. So one can see this particular illustration from the pole zero mapping. Okay. So we have plotted a very large unit circle. So we will have few zeros at this particular point. So if it is a Z1, it is located inside a unit circle. So then there should be 1, 0 at 1 by Z. Okay. So if this is a complex, obviously this is a complex 0. So then there is a complex conjugate Z1 conjugate, and this Z1 conjugate, this one, right? Z1. So if there is 0 at this particular point which is real, so this is Z2, then it's 1 by Z2 will lie here. Similarly, these are the zeros locations. Okay. So we have a 0 at this particular point, that is Z3. Then there will be a complex conjugate Z3 conjugate at this particular point, and then there will be 1 by Z3 at this particular point conjugate, and 1 by Z3 at this particular point. So these are the symmetric zero locations for a linear phase FIR filter. For a linear phase FIR filter. In the next lecture, we will discuss the frequency response of these filters. That's all for today. And if we remember this particular part for the next particular lectures, then that would be very helpful. Thank you.